Hi folks, today's video is on acids and bases. I'm going to be talking about the Bronsted-Lowry definition of acidity. Under the Bronsted-Lowry definition of acids and bases, an acid is a proton donor. This is a molecule that loses H+, and a base accepts the proton. Let's consider the acid HCl reacting with water. HCl is going to lose the proton in this reaction, and water is going to behave as the base and accept that proton. After the proton has been transferred, you're left with chloride, the anion, and water has a new hydrogen attached to it. It now has 3 bonds and a positive charge. We use the term conjugate base to describe what our acid is converted into after it has lost its proton. And the conjugate acid is the protonated form of the base. Notice that each of these pairs, the acid and conjugate base, and the base and conjugate acid, differ from each other by a proton. We're going to use curved arrows to account for the flow of electrons in acid-base reactions. And what you're going to see is that the curved arrows for the acid-base reaction will involve 2 curved arrows. Here I'm using a general equation where B with a lone pair is my base, HA is my acid. After B has gained a proton, or been protonated, it is transformed into the conjugate acid, and A is converted into A-, our conjugate base, after it's lost its proton. As I mentioned, I will have 2 curved arrows. The first curved arrow goes from the lone pair of the base to the proton, and the second curved arrow goes from the middle of the HA bond to A. What these 2 curved arrows are accomplishing is this one is showing the bond between B and H forming, and this one is showing the bond between H and A breaking and the electrons going to A. These curved arrows can be called the reaction mechanism, which is showing how electrons are moving and bonds are changing throughout our reaction. Here I want to show the curved arrows for the acid-base reaction I showed on the previous page, which is the acid HCl reacting with the base water. I'll have 2 curved arrows, going from the lone pair of my base to H, and my HCl bond breaking, and the electrons going to chlorine. I want to discuss pKa's, which is what we're going to use for quantifying acidity. Let's consider a general acid, HA, reacting with water. HA loses a proton to form A-, and water can gain a proton to form H3O+. I showed this on the previous page where A was Cl. I'm using what's known as an equilibrium arrow to show the fact that this reaction can be going back and forth between reactants and products. I'm going to define an equilibrium constant, shorthanded as KEQ, to define this equilibrium between reactants and products. And this equilibrium constant will be equal to the concentration of A- times the concentration of H3O+ divided by the concentration of HA times the concentration of water. This is always going to be of the form having the concentrations of the products divided by the concentrations of the reactants. An assumption that we're going to make is that in our equilibrium, we're going to assume that the concentration of water is constant at approximately 55.5 molar, when you perform your reaction where you have just a little bit of HA around and a lot of water. This is going to allow us to simplify our expression. We'll define a new acid association constant, Ka, as being equal to the equilibrium constant Keq times the concentration of water. Because our Keq has a term of water on the bottom, and we're multiplying by water, these terms cancel. And we're left with Ka being equal to the concentration of our conjugate base, A-, times our concentration of H3O+, divided by our concentration of acid HA. Here I've just rewritten the same Ka expression from the previous page, but I want to dissect it further. Let's consider that you have a large Ka value. What that will mean is that the numerator is larger than the denominator. You can think about that as if you have a large Ka, you have a large concentration of H3O+, and this will occur when HA is a strong acid and it loses its proton readily. In contrast, if you have a small Ka value, that means that your denominator is larger than your numerator. This will mean you have a small concentration of H3O+, you have more HA around than H3O+, which means that HA doesn't lose its proton readily, and we would call it a weak acid. For context, what types of numbers we're talking about here, when I say large Ka, it would be something like 10 to the 10th power, and a small Ka would be something like 10 to the negative 50th power. This is an extremely large range of values, and it gets to be quite cumbersome. Instead of looking at Ka directly, what we're going to do is use a log scale instead, and we'll define pKa as being equal to negative log of Ka. Once we convert our values to the log scale, then a small pKa is going to be something like negative 10, and a large pKa is something like positive 50. So acids for which you get a small pKa, these would have a large Ka and would be considered a strong acid. These will readily lose their protons to a base, whereas a molecule with a large pKa would have a small acid association constant Ka, and these would be weaker acids, less willing to donate their proton to a base. Here's a table of pKa values that I really want you to know. I won't tell you to outright memorize too many things for this course, but I believe it's worthwhile in this case. Because once you know the pKa values from this table, you'll be able to quickly determine how strong an acid is relative to another acid in the table. On one extreme, we have H2SO4, or sulfuric acid, with a pKa of negative 10. This is an exceptionally strong acid. And on the other extreme, we have the molecule C2H6 with a pKa of positive 50. This is a very, very weak acid. One really important thing to know about an acid compared to its conjugate base is that the stronger of an acid that you have, the weaker its conjugate base, and the more stable its conjugate base. And the opposite is true as well. The weaker your starting acid is, the stronger your conjugate base will be, and the less stable that conjugate base is. So an example of what a problem could look like is being asked to compare two compounds and figure out which one is more acidic. Here I'm showing an alcohol compared to NH3. What I would do is compare the pKa's of these two compounds. And the molecule with the lower pKa is going to be my stronger acid. The pKa of this alcohol is about 16, and the pKa of NH3 is 38. Because the pKa of the alcohol is lower, that means this is our more acidic molecule. If you wanted to know just how much more acidic it is, you could look at the difference in pKa's. Take 38 minus 16 to get 22. Because of our log scale, the alcohol is actually 10 to the power of 22 times more acidic than NH3. We can also use our relationship between acidity and base strength to figure out which molecule is more basic, this carbon with a triple bond in a lone pair compared to NH2-. What we would want to do in this case is figure out the conjugate acid of both of these molecules, then look up the pKa of each acid. Whichever one is the stronger conjugate acid with the lower pKa is going to form the weaker base. So, what do our conjugate acids look like? The conjugate acid of my carbon anion is this alkyne, and the conjugate acid of NH2- had a proton added, making it NH3. The pKa of the CH bond of my alkyne is 25, whereas the pKa of NH3 is 38. Because the pKa of the alkyne is lower, it is the stronger acid. The stronger acid forms the weaker base, so I know my carbon anion from before is the weaker base, and I can conclude that NH2- is the stronger base from this pair. Another thing we can do is look at a set of reactants and products to predict which is favored using pKa values. And the equilibrium position, or side that's favored, is the one with the weaker acid, or the higher pKa value. So let's look at the following acid and base. My acid is a carboxylic acid, and my base has an oxygen with 3 lone pairs and a negative charge. I'm going to draw my curved arrow mechanism. I use a lone pair from my base to form a new bond to the proton, and I break the OH bond of my acid and bring those electrons to oxygen. This would form my conjugate base, where I have an O with a negative charge, and my conjugate acid is an alcohol, the protonated form of my base. What you want to do is compare the pKa of your acid to the pKa of the conjugate acid. Here, my acid is a carboxylic acid with a pKa of about 5, and my conjugate acid is an alcohol with a pKa of 16. Between these two, the alcohol is my weaker acid, and my equilibrium is going to favor that side. I would draw in my equilibrium arrow with the part of the arrow facing toward the product as longer than the one in the other direction. If the arrow pointing toward the right is longer than toward the left, that indicates that products are favored. If the arrows are equally long in either direction, that means that your products and reactants are equally favored. And if you have a short arrow going toward the right and a longer one going toward the left, that means your reactants are favored. In addition to using pKa's to predict reactions, we're also going to want to be able to develop tools to do this qualitatively, or without numbers instead. And what we're going to do is to figure out how strong an acid is relative to another acid, you're going to look at the conjugate bases. So for a general acid HA, we're going to imagine it losing a proton to form A-, which is the conjugate base of HA. Your conjugate base is always going to have an extra lone pair compared to your HA starting material. And when we look at our conjugate bases, we're going to see how well can that particular conjugate base stabilize that extra electron density due to that extra lone pair and negative charge. If A- is stable, that means it is a weak base and it came from a strong acid. And likewise, an unstable conjugate base A- is a strong base, and that means it came from an acid HA that was weak. Let's consider a particular example of HCl losing its proton to form the conjugate base chloride anion. HCl is a strong acid, and when it loses its proton, the chloride conjugate base is very stable, meaning it's a weak base. At the other extreme, let's consider our C2H6 molecule. When this loses a proton, it forms a carbon with a new lone pair and a negative charge. C2H6 is a very weak acid, which means that it forms a very strong and unstable conjugate base. We're going to consider 4 different factors that affect how stable a conjugate base is. The first of these is considering the atom that has the negative charge. If you're comparing atoms from the same row in the periodic table, what you're going to want to do is compare their electronegativities. Electronegativity increases going from carbon to fluorine. Alternatively, if you're comparing conjugate bases that have atoms from the same column rather than the same row, you need to compare size instead. So atom size increases going down the periodic table. As an example, let's consider which is the stronger acid, this carbon-containing molecule compared to an alcohol. We'll want to think about what is the conjugate base of each of these acids. The conjugate base of the carbon compound is a carbon with a lone pair and a negative charge, and the conjugate base of the alcohol is an oxygen with 3 lone pairs and a negative charge. Carbon and oxygen are in the same row, so we need to compare their electronegativities. Oxygen is more electronegative than carbon, which means it's better able to stabilize the additional negative charge it gets in the conjugate base. This means that the conjugate base of the alcohol is more stable, which means that our alcohol starting out was the stronger acid. You can use the terms stronger acid or more acidic interchangeably. Let's consider a second example of HCl compared to HI. Here as well, and you're going to see this trend a lot, we're going to compare the conjugate bases. The conjugate base of HCl is chloride, and the conjugate base of HI is iodide. Chlorine and iodine are in the same column of the periodic table, so we need to compare their size rather than electronegativity. Iodide, because it's lower down in the periodic table, is a lot larger than chlorine. Its larger size makes it better able to stabilize the extra pair of electrons it gets in the conjugate base form, and the more stable the conjugate base, the stronger the acid it came from. So HI was our more acidic molecule in this case. Our second factor for stabilizing conjugate bases is resonance. The more resonance you have, the more stable your conjugate base is. So let's compare which is the stronger acid between an alcohol on the left and a carboxylic acid on the right. We want to draw and compare the conjugate bases for each of these molecules. The conjugate base of the alcohol has an oxygen with 3 lone pairs and a negative charge, with no resonance opportunities. In contrast, the conjugate base of the carboxylic acid has 2 different resonance structures available. You would convert from the one on the left to the one on the right by the lone pair adjacent to a pi bond resonance pattern, where I bring down the lone pair to form the pi bond and break the pi bond to form a lone pair. This resonance in the conjugate base stabilizes it, meaning this conjugate base with resonance is more stable than the other one. And our more stable conjugate base came from the stronger acid. The third factor influencing the stability of a conjugate base is called induction. This is having polar and electronegative atoms in your molecule that can withdraw electron density by having dipoles. The more you have these electronegative groups nearby, pulling electron density away from the atom that has the extra electron pair once it's converted to the conjugate base, the more stable your conjugate base will be. So let's compare 2 different carboxylic acids. One where I have a carbon with 3 hydrogens, compared to one where I have a carbon with 3 fluorines. In each case, my conjugate base has an oxygen with a negative charge, and it has resonance with the C double bond O that it's next to. So that's a commonality between these two. But the difference is at that position 1 further away. How does it compare having carbon-hydrogen bonds compared to carbon-fluorine bonds? CH bonds are nonpolar, whereas carbon-fluorine bonds are polar, with each bond having a dipole pointing from carbon to fluorine. These fluorines are tugging electron density toward themselves through the bonds. We call this induction. This induction, due to the electronegative fluorines in this molecule, stabilizes this conjugate base. And the more stable conjugate base came from the stronger acid. The last factor we'll consider is what type of orbitals the electrons are in. This has to do with the hybridization of the atom that gets the lone pair in the conjugate base. And we have to think about how close is this electron pair to the nucleus. sp3 orbitals are larger than sp2 orbitals, which are larger than sp orbitals. What this means is that sp hybrid orbitals are held tightly and closely to the nucleus, whereas sp3 hybrid orbitals are the furthest from the nucleus. The closer electrons can get to the nucleus, the more stable they are. So the smaller the orbital, the more stable the conjugate base. So let's compare in terms of acidity, this molecule on the left compared to the one on the right. And what we're going to look at is what do our conjugate bases look like? In each case, we're going to lose a proton to form a carbon with a negative charge. If I drew out my hydrogens and lone pairs in these 2 different cases, the molecule on the left has a carbon with 1 single bond to carbon, 2 hydrogens, and a lone pair, whereas my molecule on the right has a carbon-carbon double bond, so it already has 2 bonds, so it has just 1 hydrogen left and a lone pair. Now let's look at hybridization. On the left, my carbon with the single bond to another carbon is sp3 hybridized. while the carbon in my molecule on the right with the double bond to another carbon is sp2 hybridized. sp2 orbitals are closer to the nucleus than sp3 orbitals, meaning a carbon with a lone pair in an sp2 orbital is more stable than a carbon with a lone pair in an sp3 orbital. The alkene is the stronger acid that makes the more stable conjugate base. In terms of qualitatively ranking acids and their strengths, I gave you 4 different factors, and I actually presented them in their order of priority. So the biggest effect on acidity will be the atoms involved, and you'd be comparing electronegativity of atoms that are in the same row or the size of atoms that are in the same column. The next biggest factor that influences acidity is resonance. This is followed by induction, which is a more subtle effect of having polar bonds that pull electron density toward themselves. And our smallest effect is the orbitals involved, sp3 versus sp2 or sp. Our book uses the acronym ARIO to stand for atoms, resonance, induction, and orbitals. So in summary, this video talked about Bronsted-Lowry acid-base reactions, where we're transferring protons between an acid and base. I talked about using curved arrows to depict these reactions. I talked about using pKa as well as qualitative trends to predict acidity. That's it for this video. I'll see you in class.